general relativity, step by step. We've got this nice equation here, and what I want to do is to substitute for these constant terms here from our equations of state, which we've got up here. So what I'm going to do is I'm going to remind ourselves that the Hubble constant, which is a function of time, I say constant, but it's a kind of function of time, is a dot of t over a of t. And now I'm going to specify that t0 equals now, which is right now, and I'm going to require that a of t0 equals 1, and that's just a choice of units. That's not difficult at all. So what have we got? What we can do is, so the Hubble constant in these units is just a dot of t. Now what else can I do? Because a cubed, a is equal to 1, what I'm going to do is take this formula and evaluate this at now. Okay? And you remember that constant there, if I go in a little bit here, this constant here was just rho r now times a now cubed. Yeah, that's right, it's cubed, and this one was the fourth power as well. So what I'm going to do is take this equation here, and I'm going to divide by a dot squared, and I'm going to observe that a equals 1. So these terms just disappear. And what we've got left, we're going to divide by a dot squared, so that's 1 minus 8 pi g over Hubble at t0 squared, oh there's 3 of those, times rho radiation plus rho matter plus rho vacuum. Those are all now, equals k over 8 of t0 squared. So to get from this equation to this equation, we evaluate it at now. We make use of the fact that the Hubble constant is a dot over a, which is just a dot because I'm choosing units in which a of t0 equals 1. I'm choosing my units for that. Okay, so we've got 1 minus 8 pi g over 3 h of t0 squared times rho total, I guess. Yeah, let's call it total, equals k over h of t0 squared. Now you'll remember what k was. K was equal to plus or minus 1 over r0 squared, where r0 was a constant length, which I called the radius of the universe. I guess k could have been equal to 0 as well. And we could think about that at the present time. So it's pretty clear, and you see the sine of k equals an indicator as to whether the universe, whether the spatial component of the universe, universe is positive curvature or negative curvature. You remember this one was like a sphere, and this one was like a saddle, which is always difficult to draw. How does it look? It sort of goes up here. Yeah, a saddle point. So going back to this equation here, we've got 1 minus 8 pi g over 3 h of t0 squared times rho tot equals something which is, the sign of this gives you the curvature of the universe, because that's always squared, you see. It doesn't matter whether the universe is getting bigger or smaller because you're squaring it. So that tells me that if rho tot is greater than 3h of t0 squared over this 8 pi g, rho is big enough, then that means that k is negative. And if rho tot is less than this thing here, that says that k is positive. And of course, if rho tot equals 3h of t0 squared over 8 pi g, that tells me that k equals 0, which corresponds to a flat universe. Well, that's quite nice. So we call this thing here, we say that 3h of t0 squared over 8 pi g equals rho critical, because it's the critical density for the whole universe to determine its curvature. Okay? Well, that's quite nice, isn't it? Now the big question is, what's our universe? What's the density of our universe? And I'll talk about that. Well, I'll talk about the mathematics needed to answer that question in the next screencast. So I'm going to stop there. Stop.